In this video, we are going to discuss the estimation of parameters. So before we proceed, we again review the notation that we use for the mean, variance, and standard deviation for the population and for the sample. So for the population, the mean is denoted by the Greek letter mu. For the variance, this is denoted by the Greek letter sigma, and then it is squared. And for the standard deviation, the notation to use is the Greek letter sigma. The corresponding counterparts for the samples, for the sample mean, you have x bar. For the variance, you have s squared. And for the standard deviation, you have s. And our goal in the estimation of population parameters is to estimate the unknown population parameters in the first column here. And normally, we estimate these unknown values by using information from the sample. So last meeting, we were able to start already with the estimation for one mean, or the estimation of the population mean mu. We said that the best point estimate is x bar, which is just the sample mean. But if we want an interval estimate for mu, we have to consider two cases. So the first case is when sigma is known. Sigma here refers to the population standard deviation, or the sample size is at least 30. So under the first case, the 1 minus alpha 100% confidence interval for mu is given by the following formula. So we start with the point estimate x bar, and then just add or subtract what we call as the margin of error. So this is the same value in the lower limit and the upper limit. You just add and subtract it from x bar. So in our last meeting, we already have the first example, which is the mean and the standard deviation for the sample point average of 36 college seniors. And we were able to find the 95% confidence interval for mu given by 2.502 to 2.698. So going back, in order to get this interval estimate, so we start first by obtaining the z alpha over 2 value. In this case, since we are looking for a 95% confidence interval, then our alpha is 0.05. And our z of alpha over 2 would be z of 0.05 over 2, which would be z of 0.025. Again, z of 0.025 refers to the z value with an area of 0.025 to the right. Okay, so what you're going to look for in your z tables is the z value with an area of 0.975 to the left. And this value is given by 1.96. So setting up the confidence interval, you would have x bar minus c of alpha over 2 times sigma over square root of n. For this example, we are using case 1 since the sample size is 36, which is greater than 30. But since sigma is not known, we are going to use the sample standard deviation s and divide by the sample size. For the upper limit, you have the same formula except that you are adding the two terms. So plugging in the unknown values or the given values, you would have 2.6 minus 1.96 times 0.3 over the square root of 36. And on the right-hand side, you would have the same except that you are adding. And solving for these values, you will get the answer of 2.502 to 2.698. So what we are saying is that with 95% confidence, we know that we will be able to capture the population mean mu, or the grade point average of the entire senior class, by using this interval here. Okay, mahuhuli natin, we are able to catch the population mean mu using this 95% confidence interval. Now, suppose instead of a 95% confidence interval, let's compute a 98% confidence interval. So at 98%, our alpha would be 0.02. And using the same methodology, we will be looking for z of 0.02 over 2 or z of 0.01. You can try to verify using your z tables that this value would be equal to 2.33. This is the z value with an area closest to 0.99 to the left. Okay. Now plug in 2.33 into our formula. So actually you're just changing the z value. So you would have 2.6 minus 2.33 times 0.3 over the square root of 36. Okay, and on the upper limit, you just have the plus. And solving for this, you will arrive at the following. Okay, so by plugging in 2.33, we will arrive at the following confidence interval. Two 2.4835 and 2.7165. Okay, so again, this is the 98% confidence interval. And for our reference, let me just put again the 95% confidence interval, which is 2.502 and 2.698. So what you will notice here is that when we went from 95% confidence to a 98% confidence interval, our confidence interval widened. Okay? So the lower limit went lower, while the upper limit went higher. From 2.698, it became 2.71. Which makes sense because if you have a bigger confidence interval, then you should have a higher confidence level. Okay. Now, does it make sense to compute a 100% confidence interval? So number one, there's two ways that you can have a 100% confidence interval. Number one is you already have or you already know what the population mean is. Right? That is why you are sure that you can capture it with your confidence interval, which is not our purpose here. Okay? Our assumption is that the population mean is unknown. The second scenario would be you have a 100% confidence interval because you already capture all the possible values. Okay, so for example, for the grade point average, if you think of this as the GPA of DLSU students, for example, then the possible GPAs would just be from 0 up to 4. So if you set up a 100% confidence interval that says 0 up to 4, you are 100% sure that you will get the GPA of the entire senior class. However, it does not provide you any information, right? Because it is obvious already that the GPA is between 0 and 4. So normally, we want the confidence interval to be as high as possible, but we don't go up to 100%. So the usual values we go after is 90%, 95%. So as long as it is a value higher than 90%, it's already a quite a good interval estimate for us.